Imagine you got a job offer at your dream company. During negotiations, they ask you, what is your expected salary? For that position, the average salary is about $90,000, but that is usually 1 to 2 years in. When putting in your offer, should you go to 85,000, 80,000, maybe even lower? This is where knowing the standard deviation or the spread of the data would help. The average, while a useful metric, unfortunately only tells us the typical salary, but nothing about how much variation in the data there is. The standard deviation, on the other hand, helps tell us if our data is clustered around the average or is scattered. If you knew the salaries had a low standard deviation, then you can infer that most people would make close to 90,000 and you might go just a bit lower. If the standard deviation is higher though, then the salaries would vary a lot and you might even start off lower at like $80,000. In order to calculate the standard deviation for a sample, you would first find the mean if it's not already given. You would subtract the mean from each data point and then square those differences. You would then add those all up. You would divide by n minus 1, where n is your sample size, and then finally take the square root of that. Just as a side note, for a population, instead of a sample, you would divide by n instead of n minus 1. We use n minus 1 for a sample because samples usually capture less variance than the full population. And so we divide by a slightly smaller number as a correction for the small bias. And this is also known as Bessel's correction. So let's do an example. Let's take two simple sets of samples to show this, and if we were given a mean of 5 for both, then we can follow the same steps as before. First, we'll subtract the mean from each data point and then square those differences. We'll then add them all up and then divide by n minus 1, where n is 4 in this case. Then we'll take the square root. For dataset 1, the values are clustered around the mean, and we found that the standard deviation is smaller at only 2.2, where dataset 2 had a more spread out value distribution, and the standard deviation is 4.1. You could also interpret these as values as the data points being on average 2.2 or 4.1 units away from the mean. In many real-world datasets, like heights or exam scores, data tends to follow a normal distribution, or a bell-shaped curve. The height of this curve represents the probability that someone will have a certain property, like a height or exam score. So you'll see on this curve, we have marked the exam score of 75%. Since this is where the curve is the highest, this makes 75% the exam score with the highest probability of occurring in our sample. 95% and 37% are much less likely, as the height at those points are much smaller on the curve. A normal distribution also has a special property that the data is symmetrically distributed around the mean. What it also has is about 68% of data points falling within one standard deviation of the mean, 95% within 2, and 99.7% within 3. This is known as the 68, 95, 99.7 rule, and this handy property helps determine how rare a value is in a normal distribution. So let's go back to the salary example. Assuming salaries are distributed normally, if the mean was 90,000 and you found that the standard deviation was only 3,000, you would know from that rule that almost everyone in that role, which is 95% of employees, would make $84,000 to $96,000. Asking for 85,000 in this case would be a very safe bet, but if the standard deviation was high, like 15,000, the range would be much wider, and a lower starting salary might be more common. So in summary, the standard deviation tells us how spread out our data really is. If this helped, give it a like, comment, and subscribe for more quick math videos.